So I'm going to take up two problems, one a closed system and one for an open system. So we look at a closed system where we have a cylinder piston arrangement, and what this thing is that we have a piston which is over here. It's got length is L1 over there, and what we do is we heat it, and at constant pressure the piston rises from here to here. So we are looking at a constant pressure process, and the whole thing, the piston does work. And the geometrical sum initial values are given here. The diameter of this, which is circular, is 150 millimeters. Length is about 100 mm. This length L2 is double that of L1, which means it will be 200 mm. And we will look at a case where the pressure inside here is 20 bar. So P1 is 20 bar. We will solve two problems. One where there is water in this, and second where there is nitrogen. So we learned that we can have a substance which we can treat as a vapor, or we can treat it as an ideal gas. So that's the differentiation we are doing, and what we want to know is what is the work transfer and heat transfer in these processes. So the process of solving problems should begin always by making a sketch and defining the system boundary. So that's the sketch in state 1. This is the sketch in state 2. And where's the system boundary in this? So that the system boundary here is this one, and in state 2, the system boundary became like that. The system includes all the substance which is enclosed in this arrangement, excluding any of the metallic parts or any other parts that are there. So this is what it is, and we are going from state 1 to state 2, pressure constant. And to do that, we know that we'll have to heat it, and then this will go. So the first step was to define the system and get the system boundary correct. So after looking at this, it is crossing the system boundary at all with the same mass which is expanding. So important thing here is that we know this is a closed system. This is from what we have learnt in the very first module. And then we realize that if this is a closed system, the type of equations, the form of the equations that will be there is to have the control mass approach. Which means that if I have to write the first law equation for this, here we will write Q12 is equal to W12 plus E2 minus E1. It looks like a very simple thing to do, but I find that there are very many people who make mistake right here. Instead of writing this equation, they will write Q dot Cv is equal to m dot H1 plus m dot H2, all of that. So if we go wrong at this point, everything else is completely wrong. So be very clear that to understand what the system we are looking at, make the sketch and say, well, this is what it is. And this is why we will use this particular type of an equation. So now we are on the correct path here. And what we have been asked for is what is W12 and what is Q12. That's our objective. And we then proceed the same way. We say what is conservation of mass telling us? It only tells that the total mass of this and this is the same. There is no addition, there is no subtraction. So mass in the system boundary or the control mass, this is constant. We can calculate it from specific volume if that is there. No, there is a question there. We will come back to that question later. Let me just do this part. Okay, conservation of mass. Then we have conservation of energy. Okay, so the equation is the same that I have written there, and there is no assumption that is coming up in this part. And we make now we say that what are the reasonable assumptions in this application? we say that these two are such that kinetic and potential energy changes are not happening, it is stationary. The center of gravity of the system rises very slightly, and that we can neglect. So we explicitly say that we assume that delta KE is equal to delta PE, and this is 0. Which means that this E, which was U plus PE plus KE, these two terms will drop out, and we now get Q12 is equal to W12 plus U2 minus U1. And what we can see now here is that W12, this can be calculated by integrating PdV, for which we need pressure as a function of volume. In this case, we have been given P equal to constant, but that need not be the case. We could even solve the problem by saying that PV to the power n is constant, where n has a certain value. We could put that. And then this integral can be evaluated. But we need to go from state 1 to state 2, which means that we need to fully have all information about state 1 and all information about state 2. Then we say, well, how do we calculate? So that will give us the work, but to calculate heat, we need to calculate this term also. And for that, we need to know fully states 1 and states 2. We need to know all the properties in these two states. So let's see, what do we know about the states? To do that, we need to know first what is the working substance. And now we'll solve the problem, assuming that water is the working substance. And for state 1, we have been given that pressure is 20 bar, so P1 becomes 20 bar. We need a second property, and let's say that the second property is given to us that the quality of water in that is 0.8. So now we need to calculate all the other properties there. Say T1 is the first one, specific volume, and U1 and V1. We start the last one, which is straightforward, that the volume initially is pi d square upon 4 multiplied by L1, and d is given, L1 is given, you can do the calculation, and this is 1.766 into 10 to the power minus 3 meter cube. Please make sure that you write the units at every step. T1, it means that this is a saturated state. So T1 will be saturation temperature at 20 bar, and this is 212.4 degrees Celsius. Okay, then for V1, we'll get this is Vf in state 1 plus X1 plus Vfg in state 1. Vfg is Vg minus Vf. So although there are two terms looking here, but they are one and the same, all we needed to know is what is the pressure, because we know it is a wet state, and we can get those numbers from the tables, and this number is 0.0799. So we get Vf and Vg, or Vf, Vg and Vfg, all are at 20 bar. And we calculate this part. Then we will need the specific internal energy, and we do exactly the same type of a calculation. This is UF at state 1, X1, UFG at state 1, and when we do the complete calculation, this will be 2261.5 kilojoules per kg. Okay, so this is what we got now, V1 also. Now we say that to calculate U2 minus U1 that we wrote over here, we need this U2, U1 can be calculated by mass times U2 minus U1. Okay, so this is, for that we need the mass, and this could be, mass is constant in the system. So to calculate that, we now have the equation there, that M1 is equal to V1 upon specific volume at 1. And this we can calculate, and this becomes 0.022 kilograms. Now we go to state 2. Here we have P2 is constant, which is given as P2 equal to P1, so this is 20 bar. And volume, we are told, has doubled, so whatever V1 we had, or we can independently calculate this as pi square upon 4 into L2. This becomes 3.532 into 10 to the power minus 3 meters. And from there, we get that V2 is equal to twice V1. And so this tells us that this is 0.1598 meter cube per kg. Now, state 2, we got P2 and we have V2. These are independent properties, so everything is completely specified. So we have to now go back and say, well, how do I get the remaining property? Now, temperature, so we make a quick check and say, how does this V2 compare with Vg at 20 bar, which is P2? So we go to the tables and pick up Vg, and it turns out that Vg at 20 bar this is 0.09958 meter cube per kg. And what we have V2, which we just calculated here, was 0.1598, which is more than this. So this means state 2 is superheated. So we go to the superheated property tables and find out that at what specific volume at 20 bar, what is the temperature that gives that? That T2 comes out to be 435.2 degrees Celsius, and from there you can also get U2 as 3004.63 kilojoules per kg. In many property tables, U2 is not given, but H will always be given. So what we need to do is do an extra calculation. We get H there and say that U is equal to H minus PV. P and V are also given. So one extra calculation is involved if U is not explicitly given in the tables or in the property packages that we have. So we got this, and now we have everything that we needed for state 2. We can now move on and say, well, in our big scheme we wanted to calculate work. So let's write down what is the work in this process. This is integral 1 to 2 PdV, and this is P1 or P2 because pressures are both the same, V2 minus V1. So when we do the remaining calculation, this will become 20 into 10 to the power 5. Remember, this is Pascal, multiplied by the two volumes that we had, 3.532 minus 1.766 into 10 to the power minus 3 meter cube. I am writing the units at every step, so please keep that in mind because quite often people go off when they mix units. When we use Pascal and meter cube, the answer will be in joules. If it was a polytropic process, this would have worked out to be P2 V2 minus P1 V1. upon 1 minus n. And remember, this was independent of the working substance. So even though we had water here, if we said that the water was undergoing a polytropic process, this would still have been okay. But we have to make sure that P2 is in Pascal and V2 is meter cube. If you are looking, and this also should be in the same units. In case we are looking at specific work, instead of V2, this will be V2, this will be V1, in which case the units must be meter kg. So it's a good practice to write the units at every step. It takes a little effort, but then you are very less likely to make a mistake. And even if you make a mistake, that's okay. We can quickly go back and check where the mistake was if things have been done very systematically. So this, we can say, this becomes 3532 joules or 3.532 kilojoules. So this has got a positive sign. So this is work done by system on surrounding. Okay, so the next step is then we just put everything together in the equation we had right in the beginning, that Q12 is W12 plus MU2 minus U1, 3532 joules plus 0.022 kilograms, which is the mass, multiplied by the difference of internal energy, 3004.63 minus 2261.5, and these units were into 10 to the power 3 joules per kg. This joules, this also has to be joules. And when you do the calculation, this will tell us this is 19881 joules, or this is 19.88 kilojoules. So we have our answers now. The result, that the work in the process, work output was 3.532 kilojoules, and heat transfer, this is also positive, this was also positive, 19.88 kilojoules. Okay, so we have solved the problem. A couple of things to think about. Firstly, where did we get this property data from? And we have many sources. You can look up the web. There are online property tables. You can look up one book, it has got property tables, another book that has got property tables. And these numbers could be slightly different depending from the source that you have taken up. Fortunately for us, for many substances, all of them will have the same reference state. So that means for water at triple point temperature, T equal to 0.01 degrees C, HF is equal to 0 and SF is equal to 0. But still, because they all are based on data fitting and then making a curve on it, the values given by different programs will be slightly different. So instead of this, it could be within, say, plus minus 2 or 3 kilojoules per kg. That's okay, as long as throughout the problem we use the same property source. And I'm writing this because the solutions that I have provided are based on one particular source that I am using. You could be using a different one and your numbers could be slightly different. That doesn't mean that you are making a mistake. But what is important is that up to the point of formulating the equation, if you are same and okay, then you are on the right path. The numbers could be slightly off here and there, that doesn't matter, but they won't be largely different. There are only a couple of cases where numbers will be very drastically different, and that is for certain refrigerants where the reference states have been chosen differently by different sources. So what will happen in the calculation is that values of H and S and U, which are all dependent on the reference state, they will be different. values of V will be the same everywhere. That's not going to be an issue. These will be different, but don't worry too much about it, because in most of the problems, whether it is heat transfer or work transfer or say a throttling process, we are always dealing with difference of two properties, and the difference of two properties will be pretty much close to one another irrespective of what the reference temperature was. So you could have slightly different values of individual properties, but the difference in the properties will not be very much. So don't worry too much about it at that point. The difference should be matching with what we have. The second issue would be there is how much round off should be. And here again, if you round off at the first step itself from 3 decimals to 1 decimal and then calculate, the final answer could be somewhat different from what is there. That doesn't mean that you did a big mistake. Your process up to the first step was right, you are in good shape. The numbers you did, they could be slightly different. Round off you did differently, that could be slightly different. That's okay. The thing to remember is that when you look at property data or any property source, the number of decimal places that they give are there because they are confident that that many decimal places are okay. The next decimal place is in doubt. So if something gives value of say a specific value of R as 0.2978 kilojoules per kg per Kelvin, it means that 8 is okay. The next place of decimal you are not sure about. So if you are multiplying it by mass and your calculator gives you 8 places of decimal, nothing beyond this decimal actually makes sense. So you can safely truncate it or round off up to that many places of decimal that your original numbers had. But if you are multiplying this by 0.22, then now you have a problem, or you are multiplying it by 0.5, then the next decimal place is in doubt. So even if we get 4 decimal places from here, this multiplication tells you that you can round it off and keep only that many decimal places as the highest value that you have. So again, that you round it off at every step to the best possible number of significant places, and the final answer you can put it there. In the real world, this would mean we are able to discriminate 1 kilojoule in 1000 kilojoules. Rarely do we get this type of exactness in the real world of experimentation, and so you may even actually end up making some more rounding offs from further this point. But in this course, keep that in mind, make round offs at every step as appropriate. Please also make sure that you write the units at every step that you do. That way you will avoid, there are quite a few people who say that when you do PV type of a calculation, pressure they take in bar, where it should have been taken in Pascal, and the complete answer goes haywire. The process is okay, you are at least 90% correct, the last number would be only at 10%. Now we go back and say that instead of, if I had nitrogen, so nitrogen is now a different ballgame altogether, and we say that nitrogen is the geometry of the device is the same, pressure is same 20 bar. Question is, for knowing state 1, either I need to use the mass of nitrogen or the density of nitrogen or specific volume or temperature. So what we will do is we will assume that temperature of nitrogen is same as what was there in the temperature of water. Doesn't have to be though, but just for comparison's sake, it will tell us that if at the same pressure and temperature for nitrogen instead of water, what happens to the system? So we take that this is given to us. And in ideal gas equation of state, remember all temperatures have to be in absolute values, Kelvin. So we immediately convert this into 485.57 Kelvin. We will need values of the gas constant for nitrogen, maybe Cp0, Cv0. These are all given in property tables, and we take these to be constant for the entire states that the process undergoes. Okay, so then we start saying that the equations that we derive, they are still exactly the same. They do not depend on the working substance that we have. Okay, so here it is what it is. This part of the problem solving had nothing to do with what was the working substance in it, but it had everything to do with which equation we should be solving. So this process is very important. And here we will say that for nitrogen also it is exactly the same thing. Work is also integral PDV. It doesn't depend on what the material was. Internal energy change is also MU2 minus V1. This is also true. So this sheet or this part of the solution of the problem is practically independent of what the working substance was. The differences started coming in later on. So let's see what happens now with nitrogen. It tells us that the integral PDV is going to be exactly the same. We have a constant pressure process, and so this we can write as 3.532 kilojoules. If this was PV to the power n equal to constant, then we would have done exactly the same thing and written that down over here. It depends only on P2, V2 and T1, V1. So we will now also there need to know what is the final pressure and volume in the case of nitrogen, and from there we will have to calculate the work. So for that we would know what is state 1. State 1 pressure is given 20 bar. Mass we can calculate from there, P1 V1 upon RT1. We are assuming that this has got an ideal gas behavior. And throughout the process, in every state, the gas behaves like an ideal gas. So that's what we are taking here. When we put this in there, this is 0.0243 kilograms. The mass remains same in the system. In state 2, this becomes M1 is equal to M2. And so from here we can convert M into PV upon RT, and we say P1 V1 upon RT1 was mass at state 1. This is P2 V2 upon RT2. And when we solve this, we get that T2 is equal to 2 times T1. T1 has to be in Kelvin, so this becomes 971.14 Kelvin, or you can write 971.1, that's still okay, good enough. Okay, so we got T1, we got T2, and what we now need is U2 minus U1. The formula for this is same as what we had earlier. This is M U2 minus U1, and this is equal to MCV0 T2 minus T1. CV0 value will come from the property tables, and if we do the calculation and substitution, this is 8.12 kilojoules. Please remember that units have to be maintained in this calculation when you write everything. Mass has to be in kg, CV0 is say joules per kg per Kelvin, and both temperatures in Kelvin. So if this was joules per kg Kelvin, your U2 minus U1 will be in joules. If initially we took it at kilojoules, we must consistently keep kilojoules and make sure the final answer is also in kilojoules. So this is, we get the change in internal energy, and substituting that finally in Q12, this becomes W12 plus U2 minus U1, and this is calculated as 12.45. Please remember that when we write this or we write kilograms, this K is always a lower case. It should never be a capitalized. So writing kilojoules as kj or kilogram as kg, both are wrong. Okay, so we solved the problem, and you can see that this solution methodology was different. We used a different set of things. The main thing was equation of state, and the same process for two different substances we have been able to solve it.